In my last video, I talked about the general application architecture of a tactics game that I'm building using Godot. Now let's dive a little bit deeper into the development of units and some of the techniques I'm using and oddities I've ran into with them in these early stages. First off though, if you'll recall, I showed off two different prototypes, a sci-fi pixel art game and a Kaiju Clash spin-off. Well, I've decided to focus on the build your own monster them up Kaiju Clash spin-off going forward. The general idea will be to build up a team of mega monsters cobbled together from various parts, each with unique abilities and stats, and travel to different themed arenas around the world on your path to global glory. I've decided to go this direction over the sci-fi game as I've got some bigger ideas for that one that I want to let stew for a little bit longer. With the Kaiju Clash spin-off though, I can take the design aspects from that game that worked, along with a whole bunch of ideas left on the cutting room floor, and give myself a head start on this one. As I feel Kaiju Clash probably should have been a tactics game instead of a turn-based battler anyways, there's no shortage of ideas to build off of here. This will save me some time and effort early on and let me focus on the technical aspect of building out a full tactics game. So with that established, let's talk a bit more about how units are implemented. As a quick refresher, here's how units are structured. Controllers are responsible for some singular aspect of a unit's operation, like resolving actions or playing animations, and action overrides are for actions that don't fit neatly into my regular action resolution flow. Check out my other video, which will be linked below if you want to learn more about these two pieces, but the remaining items I'd like to talk about are how unit data is structured and loaded, what details art implementation is hiding, and how the AI controller works. First up, let's talk data. There's a few requirements that drive how unit data needs to be structured. The first is that teams will have a variable number of units. Second, each unit will be composed of 3 parts, a torso, arms, and legs, although arms and legs are used a little bit fluidly here since wings, tentacles, and whatnot will also be in the game, but the idea remains that there is an upper torso attachment and a lower torso attachment. Next, while still in the early design stages, I'm going to explore having feats, XP, and other unique information on parts. Therefore, every part should be unique from every other part, even if, for example, they're both gorilla arms. And lastly, the player should be able to shop for parts, assign them to units, and swap parts between units. Therefore, units need to be flexible and dynamic in regards to any data related to their parts. The key idea behind all of these points that you may have noticed is that data will be fairly dynamic. So to support that, there's 3 layers to unit data: battle parties, unit definitions, and part definitions. Battle parties are the simplest data structure as they're just containers holding references to the units that belong to a specific group of combatants, such as the player's units, so that other components can access as appropriate. In fact, at this point in time, what's on screen now is the entirety of their code. Unit definitions are where the data for a specific part are defined and held, along with a few helper functions. This consists of the name for that unit, the parts that it holds, and functions for dealing with adding and removing parts. This is, again, not a particularly complex data structure, but it helps ensure that unique data has a place to live. The only assumption made is that of the core unit structure of torso, arms, and legs. Part definitions are, as the name would suggest, where parts and a variety of data related to them are defined. This includes both globally constant data, such as the maximum value any part can have, and local data, such as the stats for a specific part instance. For example, at the top of the file are constants defining how stats should scale as a part gets stronger, and enumerators for defining exactly what type of part a specific instance is. After that, the variables specific to a part type are defined, such as its elemental class and stats. It's also worth noting that each part does have a fixed resource it pulls unchanging data from, such as where its animation instance lives and what its base stats are, to make iteration easier. So there exists a fixed lobster torso part definition, for instance, that defines this base information. When I need to instance a unique torso, that new part will copy the unchanging data from this base resource and then apply its customizations on top of that base data. Part definitions also contain a few helper functions, such as formatting the name to use for a part in the UI, and handling stat scaling, though most of these functions are still very basic and will be iterated on later. And that's a look at how unit data is managed in the game. Battle parties contain units, units contain parts, and parts contain the bulk of actually useful data. And so now that we know how units are defined, let's take a quick detour to talk about art, as art for the monsters is unfortunately not as straightforward as just layering some images on top of each other. The first thing to note about parts is that each part has a scene that it can instantiate for rendering and animation. This scene holds things like sprites, animations for each move, and defines attachment points, which are simple 2D objects that define how parts should snap to one another. So each torso has attachment points on it located where each arm and leg should attach to it, and marked for the appropriate limb. And each arm and leg has a matching attachment point with artwork placed relative to that location. When a limb gets attached to the torso, these 2 points line up the artwork appropriately, and as long as I make sure that my animations are relative to their attachment point, I end up with a flexible system for letting parts connect to one another in whatever way they deem fit. Parts also have the option to sync their positions with one another. So the torso, for instance, can tell the arms and legs to move with it for normal use, but if another part needs to override this at some point, maybe so a character can jump in the air and coordinate the rest of the body with the leg animation, that's also an option. Beyond those 2 features, part scenes are really just art containers. I used a similar but simpler implementation in Kaiju Clash and was generally satisfied with this approach, as I found each part tended to have unique needs, whether that be animating with skeletal animations versus simple cutout style rotations, or just so I could add custom particles and sound effects easily. Unlike Kaiju Clash though, getting parts to layer correctly proved to be more complicated than just adjusting the Z-index on each part. That works fine for adjusting parts relative to each other on the monster, but it turns out that Z-indexing in Godot does not play so well with Y-sorting, which is also a requirement since I want environmental objects to be able to partially obscure monsters and other game objects. When you have both Z-indexing and Y-sorting active in a scene, the end result is that objects with the default Z order of 0 get Y-sorted, but those with non-default values don't. There's 2 main ideas I've been considering for getting around this issue. The first, and what I currently have in the game as it was the fastest to integrate with my existing implementation, is to render the final collection of parts to a sub-viewport. In case you're unfamiliar with sub-viewports, they're basically Godot's way of doing a render to texture from within the scene tree, which means you can take advantage of nodes, sub-scenes, and other Godot goodness. This solves the issue as now I can order parts based on Z-index inside the sub-viewport, and then let that get Y-sorted. The biggest downside to this approach is that since the parts no longer exist in the main world, particles or other effects that may go outside the viewport get cut off, which means I have to either make the viewports larger or dynamically instantiate these items outside of the viewport. There is, of course, also the performance downside of rendering all those extra pixels, but my games aren't exactly pushing the limits of graphical fidelity, so while I will performance test this at some point, I don't anticipate this will make or break the game for most systems. The other idea I've considered is to duplicate the parts container and have one copy sit higher in the scene tree for parts that should be in front, and the other sit right behind it for parts that should be in the back, and maybe even add a third instance as a middle layer. I could then choose what to render on a per artwork basis depending on which container it resides in and where it should draw relative to other parts. This is potentially more performant and flexible, but I would have to dynamically disable sounds, particles, and so on for containers that are not the primary container. There's also a bit of added complexity around coordinating part positions and animations across multiple scenes representing the same thing, and the fact that I'd be locking myself into a fixed number of layers that parts could fall into, which is potentially problematic as some individual parts are actually composed of several layers of graphics with specific ordering requirements. It's not the end of the world to deal with all of this, but there's enough downsides that I'm not convinced it's the right call. If you can't tell, I'm not sold on either solution, and I expect I'll be revisiting this issue as development progresses, so if you have any thoughts, please let me know. But that's enough art talk for now, so let's instead talk about the AI controller and how opponent units decide what to do. Since most opponents will be composed of a random assortment of parts, I needed to implement an AI system that's flexible and adaptive since I won't know what actions the unit will be able to take ahead of time. If you've been around here a little while, then you might already know where this is going. Utility AI. I've talked about this concept previously, and we'll link to that video below if you want the full explanation, but the high-level overview is that utility AI is a way to let an entity score each potential action it can take based on the current game state, and then select the best action based on those scores. You can apply weights based on changing priorities, add some randomness to the mix, and apply a whole host of other modifiers to make things more interesting, but the core idea is still the same. Score potential actions and choose the highest scoring one. In this game, each action a part can take has a utility score attached to it, which means that when a unit needs to pick an action, it gets some helpful data together and then lets each action tell it how useful it is. Specifically, my implementation is a form of infinite access utility AI, which is a concept Dave Mark has introduced and spoken about across a few different GDC talks over the years. It's essentially a framework for implementing utility AI based on the idea that you'll probably want to add, remove, and tweak parameters for action scoring as development progresses, and will therefore need a system that's inherently flexible with how it handles everything. The framework is also intended to be friendly to non-technical users, but since I'm doing pretty much everything except for the art for this game, I do take a few shortcuts over his more robust implementation. The ideas behind his system and mine are still the same though. Each action has a list of concerns it wants to score, such as the distance to a potential target, how much damage an attack is likely to do, and so on. It normalizes and plots the score of each concern independently along a curve, and then combines those scores together to get a final score for the action. The AI controller, which is really just a lightweight entry point to this system, can then pick whichever action scores the highest, or maybe choose a random selection from top scorers if it's close, and then pass this selection over to the action controller for execution. If there's more than one option an action can take, such as 2 units are in range but the action can only target 1, each option is scored internally by the action, and only the best scoring option is returned for consideration by the AI controller. To go too much further in depth on the implementation side would involve summarizing a few hours of GDC talks, which I will link down below for you, but the general flow ends up looking like this. Let's look at how a unit would score using a pinch attack from the lobster arms. This is a simple attack that is only concerned with how much damage it will do against a target. Upon beginning action selection, the AI controller makes a context object, which holds information such as the list of active enemy units and the unit taking the action, and passes this object to the action's decision maker. The decision maker will then look at which units are in range for this attack and score the attack against each in-range unit. For each potential target to attack, how much damage the action will do to the target as a percent of its total health is calculated and plotted along a curve. Whichever target produces the highest score will be returned by the decision maker as the best this action can do right now. This potential action will then have to go up against all the other actions for selection and execution. For an action that has multiple considerations, the process is the same. The action scoring step just adjusts its score based on the plotted value of all considerations, typically by averaging together all these different scores, though some actions can choose to use a different formula. And that's gonna wrap up how units work in this game. Thanks for watching, and as always, please reach out with any thoughts or questions.